So, you know, if somebody can just remind me at like 9:40, 9:30 to start passing out the attendance sheet, we'll take the attendance at the end of class today. Okay, so we're now going to enter chapter 8. Okay, and chapter 8 introduces a statistical method called hypothesis testing. Okay, so and just in case you're curious, if you have the second edition of the textbook, we are skipping section 7.4. Okay, so we've covered up through chapter 7.3 in or section 3 in chapter 7. I'm sorry, 7. We're skipping 7.5. So we got through 7. We got through 7.4, but we are skipping section 7.5, 7.5. Okay, so in chapter 8, we will do hypothesis testing, and we have a question. I have. Let me. I'll try it again. Okay. Okay. So in chapter 8. We are doing hypothesis testing, which is a tool we use to answer questions about the population. Okay, so you know, we will we use this being hypothesis testing. As a tool questions about the population based on samples we observe. Okay, and the way it works is we start off. So I'm going to kind of just list the outline of how hypothesis testing goes about, and then we're going to go into depth into each of these steps. Okay, so there are, I guess, 4 parts to hypothesis testing. And we start by create hypotheses. Okay, and they always come in pairs: a null hypothesis and an alternative hypothesis. And I'll go into depth into each of these steps. Okay, so just write this down: a null hypothesis and an alternative hypothesis. Okay. And then part 2 is called preparation, and this involves choosing a significance level, also known as alpha. Okay, and then kind of just, you know, preparing your data, or just making sure the data is okay. So, you know, check and label your data. Okay, and then we're also supposed to check the conditions of the central limit theorem, which and so we'll again, all of these things we're going to explain in detail. Okay, then we do calculations Okay, and specifically, the value we are going for is that we want to find something called a p-value. Okay, and generally to find the p-value, this involves finding the standard error and the test statistic. And then lastly, we interpret and make conclusions. Okay, so these are the pieces of hypothesis testing, and we'll go in depth for each of these things here. Okay, and so here's kind of the overview of hypothesis testing. If I'll just make sure I can flip on to the next page here. Looks like some of you guys are still writing, but looks like for the most part we're okay. All right, so here's kind of the big picture idea. Okay. Let's say you're playing a game. I don't know, you go to a carnival game. You're playing some kind of carnival game. Okay. And sometimes when they run carnival games, sometimes there's some trickery involved, and maybe the games are rigged. Okay, so the game you play, it's supposed to win half the time. Okay, so okay, it's like they've claimed that the game should win, 50% of the time. Maybe it's like you spin a wheel and half of the spaces are winners and half are losers, or something like that. Okay, who knows? Okay, and let's say you play the game 10 times. Okay, so you decide to so I'll say you decide to play the game 10 times. Okay, so if the game is fair, how many times should you win? You should win 5 times, right? If the game is fair, you should win 5 times. Okay, let's say you only win 3 times. So, but what happens is you only win 3 times. Okay. Well, are you then going to go out and say, don't play this game, it's rigged, I played it 10 times, I should have won 5 times, but I only won 3 times? Are you going to say, this game is rigged? Or is it possible that you just got unlucky? It's definitely possible that we just got unlucky, right? All right, so, can we now claim that we have evidence that the game is rigged. So we win less than 50% of the time. This is the question, okay? And I think our answer here is no. Does it prove that the game is not rigged though? No, it doesn't, right? You know, the fact that I got 3 wins out of 10 doesn't prove that the game is rigged, but it also doesn't prove that the game is fair either. It's just you only played it 10 times. There's not a whole lot you can say, okay? So the answer here would be no. We could have just been unlucky, right? Unlucky, okay? So this does not prove that the game is, you know, does not provide evidence that it's rigged. That the game is rigged. Nor does it show that it is fair, okay? Is that okay? The logic behind this? Everyone's okay with this statement? Yeah? Okay, so, but let's say we decide to do a more rigorous thing, okay? So now we play let's say 200 games. Okay? Now, if we played 200 games and the machine is fair or the game is fair, how often should we win? Okay? So we should win 100 times. Okay? But what happens, we should win 100 times if it is fair. Okay? But what happens, we win only 60 times. Okay? So, you know, over here, when we played 10 games, we won 30% of the time. And over here, we played 200 games, we still won 30% of the time. Okay? However, if I ask the same question, can we now claim that we have evidence that the game is rigged, so we're winning less than 50% of the time? What would you say? And why are you guys saying yes? Okay, so in our instinct, right, in our gut, we already have this idea of kind of what's going on, right? So when we played 10 games and we won only 3 times, we just said, meh, oh, I probably got unlucky, okay? When we played 200 games and we won only 60 times, is it possible that we just got really unlucky? It's possible, but I would have to be really, 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 really unlucky, okay? Right? There's something in us that says, hey, if I play 200 games, sure, I should be winning around 100, and yeah, I might win a little bit more than 100 games, I might win a little bit less than 100 games, but winning only 60 games? That doesn't feel right, okay? There's something in us that says, this doesn't feel right, I feel like the game is rigged, okay? And we can actually do the math and we can say, hey, if the game were playing fair, what is the probability that I would only win 60 games out of 100? Okay? And it turns out that probability is incredibly small, meaning I would have to be incredibly unlucky for me to win only 60 games out of 100. And so we say because it's so unlikely for this to happen, I'm going to say I have evidence that the game is rigged. Okay, so over our gut was yes. Okay, we have evidence that the game is rigged, but the logic behind coming to that conclusion is a little bit. It feels a little bit roundabout, but I'll write it out. Okay, so we have evidence that the game is rigged. How? Okay, so I'm going to copy this over onto the next slide. Okay, so we've played 200 games. We should win 100. We only won 60. Okay. So, how do we know, or how can we say that it's rigged? Okay, well, what we do is we say, okay, for argument's sake, let's say the game is not rigged. Okay? And that means I had to be very unlucky to have won only 60 times out of 200 plays. Okay? And in fact, we can do these calculations, okay? In fact, I can do the calculations. Okay? And the calculations are the types of questions we asked in Chapter 7 and that were covered on today's quiz. It was, we could say, you take a random sample of 200 games. Every game has a 50% chance of winning. What's the probability that you get a sample where only 30% have won? Okay? So in fact, I can do the calculations. And I'm going to just kind of frame it this way. So you play a game 200 times. Each game, if it's fair, has a 50% chance of win. Okay, what is the probability you win 30% or less? Okay, and so you do your standard error calculations, your z-score calculations, and look that up in the table. Okay, and anyway, so that resulting probability, okay, in fact I can do the calculations, and the resulting probability is very small. Maybe it's, let me just kind of see what kind of answer it would come out to be. Yeah, I'm getting a z-score of -6. Okay, so I'd say less than 0.0001. Okay. So at this point, is it possible? Technically, it is possible that I got really unlucky. However, it's so incredibly unlikely for this to have happened. I'm ready to say I don't think I got that unlucky. Instead, I'm going to conclude that the game is rigged. Okay? The resulting probability is very small. It is so small that we will ignore the possibility that our results were from chance alone. Okay, we conclude that the game is rigged. Okay, so I just kind of want to make sure that this line of reasoning makes sense. We have a question.
What's the line that you decide that it's so small?
Oh, that's a great question, and we will talk about that. That's when we said part 2 and we pick a significance level. That significance level is that line, exact line that we're talking about when we say what's small and what's not small. Okay? Yes?
So if we were to do the standard error, we would do 0.50, parentheses 1 minus 0.50 divided by 200.
Exactly, exactly.
And then do the z-score.
And then we would get a z-score, where we would do 0.3 minus 0.5 over our standard error. Exactly.
That's how you figure it.
And then you look that up in the z-table and you get it up. Okay, so you already got the kind of process in your mind here. Okay, so yes, but the logic behind this thing, where we're saying I'm going to conclude that this game is rigged, is we say, hey, look at my data. My data, I only won 30% of the time. If it were fair, I should be winning 50% of the time. Okay, and what we say is, well, okay, for argument's sake, we're going to pretend that it's fair. If it were fair, what are the chances that I get the data that I observed? Okay? If that probability is very small, then we say, I probably didn't get this data from random chance alone. I mean, it's possible that I got it from random chance, but it's incredibly unlikely. Okay? On the other hand, if it turns out that there's a pretty high probability of getting our data from random chance, then we say, well, maybe it happened by random chance. Okay, maybe I just got unlucky. You know, when you win 3 games out of 10, you just say, well, that kind of sucks. All right, it's not proof that the game is rigged. It's not proof that the game is fair, but it's not proof that the game is rigged. However, if you play 200 games and you only win 60 games, then that's a lot more compelling evidence. Okay, so this is kind of the big picture logical reasoning that we have in hypothesis testing, and I just kind of want to make sure that this sort of makes sense. Okay, so this value, this resulting probability, where we say, okay, for argument's sake, let's pretend this is the case, then what is the probability I get my data? That is called the p-value. Okay, so in hypothesis testing, which I'm going to just abbreviate HT now, we say, for argument's sake, let's assume, et cetera, et cetera, et cetera. Okay, and the thing we're assuming is like, the game is fair, or whatever it might be. Okay, the thing that we're assuming, this is actually called the null hypothesis. Let's assume the null hypothesis is true. So when we say, for argument's sake, let's assume the game is fair, the generic term for all hypothesis testing is, for argument's sake, let's assume the null hypothesis is true. Okay? And if that's the case, what is the probability that we observe our data from random chance alone? So, for the game examples, what's the probability? If the game is fair, what's the probability I only win 60 games out of 200? Okay. Okay, and this resulting probability is called the p-value. The probability, okay, that answers our question is the p-value. Okay, so if the p-value is a probability, what's the biggest number you can get for the p-value and what's the smallest number you can get for a p-value? 0 and 1. So the p-value is always going to be between 0 and 1, okay? So the p-value is a probability, so the p-value is always between 0 and 1. So if in your work you ever get a number outside of 0 and 1, you know you've done something wrong. Okay, the probabilities are p-value, and so here is the definition of the p-value. The p-value, this is the probability of observing our data, and we have to include this phrase, or something more extreme, or I would say, or something more unusual, if we assume that the null hypothesis is true. Okay. All right, so let's try an example, and we'll work through all of our pieces here. Okay, well here let's do the same type of thing. Let's say you play 80 games at the carnival. Okay, and the game has a 50% probability of, the game claims to have a win rate of 50%, okay, but instead you won only 30% of the time. Okay, so in other words, 24 wins. Okay, so you won only 30%, or you won only 24 times. Okay, can we suspect that the game is playing fair, and we got unlucky, or does this provide evidence that the game is rigged against us? Okay, well, let's see. Rigged against us. Okay. So, all All right, so let's go through this, okay? So part one is creating our hypotheses, okay? So in words, we have a null hypothesis, which is going to be H0, and this is the game is fair. Okay, the win rate really is 50%. Okay, the alternative hypothesis, because our hypotheses always come in pairs, would be what? The game is unfair, or the game is not fair, and we would think that the win rate is what? Not 50%, but somehow it's rigged to be lower than 50%, right? Okay, so I've written these out in words. When we do hypothesis testing, a lot of times we use symbols to kind of shorthand what we're going for. Okay, so we will just say P is the win rate, and so our null hypothesis will just look like this. P is equal to 0.5, and our alternative hypothesis is that P is less than 0.5. Okay, notice that when I write the hypotheses, I'm putting colons here and I'm not putting equals. So it's not, don't write the null equals 0.5. That's no good, okay? There needs to be a symbol, something like the null hypothesis says that P is equal to 0.5, okay? Don't do this. Don't say null is equal to 0.5. So this is bad. This is good. Okay, is that all right? And then, so part two is preparation. Okay, so we have to choose a significance level. The alpha is our significance level, and this is the line that we draw, and we say, hey, if my probability is less than this number, I'm going to conclude that that it didn't happen by chance. And if my probability is bigger than this number, I'm going to conclude that it could have happened by chance. Okay? Now, we can, you know, if you want to be kind of accusatory, and if you're like more ready to jump on the claim that it's rigged, then your alpha will be something high. Okay? And if you want to be very cautious about, you don't want to make any kind of false accusations against this, and you know, of course, depending on the situation, you know, it might not be accusations, but we call this either rejecting or not rejecting the hypothesis. You might want to choose a small significance level, okay? And so kind of the default significance level is to use alpha equal to 0.05. Okay, so alpha is most often something around 5%. Okay, and then we'll look at our data. And our data, what do we have? We have our sample size is 80, and our the number of wins is 24, right? So this says my sample proportion p hat is 24 over 80 is 30%, okay? Which it was also stated in our problem. So our sample proportion is 0.3, okay? And what else? I guess this is not from our data, but what is the proportion that is stated in our null hypothesis? This, we call this P0. This is what we should be winning. We should be winning 0.5, okay? So this P0 is, so let me just kind of label this P hat. This is our sample proportion. And 0.5, this is the proportion in our null hypothesis. Okay, so we should be winning 0.5 of the time. What we actually did, what actually happened was we won 0.3 of the time. Yes?
Is the default significance given to us, or we have to find it?
The default significance level is just 5%. Okay, so that's like, if you ever do a problem in the future, sometimes the problem will say, use this significance level or use alpha equal to 10%. If it doesn't say anything like that, just assume it's 5%. Okay? So just assume it's 5%. Otherwise, use whatever's in the prompt. Maybe I should just kind of a little tip for hypotheses is that the null hypothesis will always have an equal sign. Okay, so the null hypothesis will always have an equal sign. Okay, the alternative will have either greater than, or less than, or not equal to. All right, and you'll use the same number. You know, if the P0, the number that appears in the null hypothesis is 0.5, that same number will appear in the alternative as well. So really, when you come to making hypotheses, at least when we get started here, is to just first you got to figure out this proportion and then which sign to use in our alternative here. Okay, is this part okay? All right, so then we're going to go on to our next part, which is the calculations. Okay, and so what we're going for is we want to find what is our p-value. Okay, this is going to be what is the probability of observing our data if the null hypothesis is true. Okay. Okay, and so in our case it is what is the probability that we win 30%, okay, or less if the true win rate is 50%, okay, and we play 80 games. Okay, so what we have is kind of a problem that we did in chapter 7, or you kind of had this on your quiz. All right, and so you have n equals 80, p hat is equal to 0.3, and here we're going to have p0 equal to 0.5. So what we have is a normal distribution, okay, So whenever we play the game, if we play 80 games, I should be winning about 50% of the time, okay? But of course, because of random chance, maybe I win a little bit more than 50% of the time, maybe I win a little bit less than 50% of the time. And now the question is, well, is 30% win, is that reasonable or is that unreasonable? Okay? So I should be winning 50% of the time. And the question is, is 30%, pretty close to 50 where it happens quite often, or is 30% far away from 50 so it happens very, very seldom? So what we want to know is, what is the probability that we get 30% or less? This is what we want to know. Okay, because this is what happened to us. We only won 30% of the time. Is this a likely outcome? That's what we want to know. Okay, so we've got to figure out our standard error. So what's our standard error? Okay, our standard error here is going to be P0 times 1 minus P0 divided by n. Okay, notice we do not use p hats. Okay, don't use the p hats for here. Okay. Do not use p hat. So in our case, what we're going to put here is going to be 0.5 times 1 minus 0.5 over 80 inside our square root. Is that okay? So I'm going to do 0.5 times 1 minus 0.5 divided by 80. And take the square root of this, and I get 0.0559. So far, so good? Okay. All right. How do I get my z-score here? Okay, well, but what does the operation have to do first? 0.3 minus 0.5 divided by 0.0559, exactly. Is that good with everybody? So I'm going to have 0.3 minus 0.5 divided by 0.0559. And I get negative 3.58. Yeah, and now we look it up at the table. But based on this, does this seem like an extreme z-score? Yes, right? Because we said anything farther than 2 standard deviations away is pretty rare, okay? And if we're more than 3 standard deviations away, that's really rare, okay? Here I'm about 3.5 standard deviations away. I can look this up in the table and we can see what it says. All right, so we'll, what do we want? So we're going to go to, I want the negative side. Actually, oh, my table only goes to 3.49. So the value I got is off the charts, literally. So this is, not on the chart. The smallest value that shows up on the chart is 0.002, okay? Okay, which means, so that means if this, if this is the most extreme value that shows up on the chart and I'm even farther away than that, this means my p-value, associated probability, must be even smaller than this. Huh? Yeah, so the p-value is even smaller than 0.0002. Okay, so that's like 2 in 10,000. Okay, it is possible for someone to play 80 games and win only 30% of the time by bad luck. It's possible. But they would have to have very, very bad luck because it happens less than 2 in 10,000 times. Okay? So we can say, well, I could have been one of those 2 in 10,000. Or I can say, I think this machine is rigged. Okay? And so I think what we would say agree is that I don't think I got that unlucky. Instead, we're going to conclude that the machine is rigged. Is that okay? So the p-value that we have is smaller than 0.002, so our conclusion, okay? So, what we have is, so this is technically how our conclusions work, is we compare our p-value to alpha. Okay, so what we say is 0.002 smaller than 0.05? Yes. Then alpha, 0.05, which is alpha is 0.05. That's what we established in step 2, is 0.0002 smaller than 0.05. The answer is yes. So then we reject the null hypothesis. Okay. So I'm going to flip over to the next slide and we'll work through this.
You said alpha is always going to be 0.05?
If the problem doesn't say what alpha or what significance level to use, then assume it's 0.05. Okay? But sometimes the problem will say use significance level of 1% or use significance level of 10% or something like that. So sometimes the problem will say use this level alpha or use a different thing. But if it doesn't say anything, you can assume it's 5%. Yes?
So if our p-value is smaller than 5%, if otherwise stated different value,
Yeah.
so we always reject it?
Yeah, if your p-value is less than 5%, you can reject the null hypothesis, okay? Or basically the rule, and so did everyone get this down? I'm going to flip to the next page. And what we're going to say is, so our, for part 4, our conclusions is that if the p-value, and this is always the case, if the p-value is less than alpha, we reject the null hypothesis, okay? And we would say, we have evidence that, whatever, whatever the alternative hypothesis, whatever HA says, is true. Okay. On the other hand, if the p-value ends up greater than alpha, we do not reject the null hypothesis, okay? And it's important that we say we do not reject the null hypothesis. Don't write we accept the null hypothesis, okay? There's a distinction here, okay? We do not reject, and we'd say we do not have evidence to say that, the null hypothesis is false. Okay, so in our case, our example, our p-value is 0.0002, our alpha is 0.05, our p-value is less than alpha. So we reject the null hypothesis, and what we say is we have evidence that, and our alternative hypothesis was that the machine is rigged against us, or the game is rigged against us. Okay, rigged against us, so we win less than 50% of the time. Yes, question.
Yes, sir. So we always just follow these 4 steps?
Yes, pretty much. Okay. So let's take a 10-minute break here. We'll come back. We'll work through another example, and then we're gonna make our lives a little bit harder and try another expand upon this idea with 2 populations. Okay.